Welcome to Mrs. Neller's notes for her pre-calculus class. These are the notes for section 12.1, day 2, entitled Sequences and Summation Notation. And today we're going to talk about the last two objectives. We're going to talk about what a partial sum of a sequence is, and then we're going to talk about sigma notation. And for a partial sum of a sequence, this is when, remember, we have any sequence where the terms are a sub 1, a sub 2, a sub 3, and so on. And the partial sum is where you take the sum of the first term. So the first partial sum is just that first term. The second partial sum is the sum of the first two terms. The third partial sum is the sum of the first three terms, and so on and so on. And you can do that for as many terms as you'd like. So when we have that sort of a situation, that's considered a partial sum, or the sequence of partial sums. And let's practice that. Let's find the partial sum of the first n terms in the sequence, the first four terms. There we go. So let's find the first four partial sums. So in order to do that, we need the first four terms. So we're going to find a sub 1, which would be 1 over 2 to the first. So that'll be 1/2. And then a sub 2 would be 1 over 2 squared. So 2 squared is 4. And the third term would be 1 over 2 to the third. 2 to the third is 8. For 8, so we'd have 1/8. And then 4, a sub 4 would be 1 over 2 to the fourth, and 2 to the fourth is 16. So there's our first four terms. And then to find the sum, the first four partial sums, we need to, well, for the first one, we don't really do anything. We just write down the first term. But for the second partial sum, we add the first two terms. So 1/2 plus 1/4, which would be 3/4. So this is our first partial sum. That's our second partial sum. Here's our third partial sum. So we'll need 1/2 plus 1/4 plus 1/8. Whoops, plus 1/8. Now we already did 1/2 plus 1/4. That's 3/4. So now we add 1/8 to it, and we get 7/8. And then for our fourth partial sum, we add up our first four terms. And really, that's the first four that we wrote down, the only four that we wrote down. And again, we just found the first three, and then we're going to add 1/16 to it. So we're going to add 7/8 plus 1/16. So that's 15/16. Now notice that these sums, as you keep going, as you keep adding more and more and more, they get closer and closer to 1. So that's going to happen when we're dealing with our partial sums. They're going to approach 1. Now you're going to have problems like this in your homework as well, and then they're going to ask you to take it a step further. They're going to ask you to write the nth partial sum. So when you're writing the nth partial sum, they'll give you the sequence. They'll give you 4 of those, or 5 of them, or 6 of them. Okay, so we're going to have to take a look at the numerators, and then we're going to have to take a look at the denominators, and we're going to have to try and find a pattern. So let me write over here, when we're going to write the nth partial sum, I know it wasn't in the directions up above, but you will have to do this in your homework. And we're going to take a look at our sums here then. We're going to take a look at our 4 sums, and we're going to find that pattern. So if you look at your numerator, you're going from 1 to 3, and then 3 to 7. So to go from 1 to 3, we're adding 2. To go from 3 to 7, we're adding 4. To go from 7 to 15, we're adding 8. So what we're doing there then within our sums is that we have another pattern here where we're multiplying by 2. So this is where we have a double pattern where the first layer is the addition and the second layer is the multiplication. So in the notes for 12.1, day 1, we talked how that means that we're going to have a base of 2, and then we're going to have an exponent of n. So anytime that happens, that's the situation that we're going to be dealing with. Now we want to check it though and make sure it actually works. So my first numerator that I should get out should be a 1. So if I put 1 in here for my first term, 2 to the first power would be 2. And if I check it with my second term here, I'd want 3. If I put a 2 in there, 2 to the second power is 4. So I'm 1 away from each of those. So I'm going to adjust my function by subtracting 1. And then for our denominators, let me do that in a different color here. We're going from 2 to 4, and then from 4 to 8, and then 8 to 16. They're getting multiplied by 2 every single time. So there, our denominator is going to just be 2 to the n. Because when we have repeated multiplication, that's when we're dealing with exponents. So what we multiply by becomes our base. So we can check it as well. If we did 2 to the first power, that would be 2. 2 to the second power, that would be 4. 2 to the third power is 8, and so on. So then this is what we would call our partial sum for the n terms. Okay, so when you see that in your homework, remember that's just using the same rules that we talked about in the previous section of notes to find patterns for that function that describes the whole sum in this case. All right, now let's talk more about the sigma notation. And when you have a sequence, we can write the sum of the first n terms using summation notation or sigma notation. And the notation comes from the Greek letter sigma. Whoops, I meant to underline. Right here, the Greek letter sigma, and it means sum. So you can call it sigma notation or summation notation. And there's some rules for what each part here means. But you have your sigma. You're going to have k equals some value, and it won't always be k. It could be any variable, but that's your starting value. And for some reason it won't let me write. That's your starting value. And then the n on the top is going to be where you stop, basically. So the k equals 1, that's your first value, and then the n, that's going to be your stopping value. And the sigma tells you you're adding, and then what is in the right side, or to the right side of the sigma, this a sub k, that tells you your function that you're going to be using. So you're going to get your first term, your second term, your third term, and then you're going to add them all together. So here on the next slide, they explain that as well. So the way you read the sum here would be that you have a sum of a sub k from k equals 1 to k equals n. But I don't know why they don't put k equals n up at the top. They just don't. So the k is your index, and again, it doesn't have to be a k. It could be any variable. And basically, you're going to substitute that value into the function that's on the right side of the sum. So again, the value on the bottom is where you start, the value on the top is where you end, and we're summing, and then this is the function to get all of the terms that we're going to sum together. So it looks more complicated than it really is. So let's take a look at a couple examples here. So for our first sum, we have the sum of k squared, and we're going to start with 1, and we're going to go to 5. So that means I'm going to take 1, and I'm going to substitute it into this function, k squared, and I'm going to do 2, and then 3, and then 4, and then 5, and I'm going to add all of those together. So I'm going to take 1 and substitute it in, and then I'll add it to 2 when I substitute it into the function, and then 3, and then 4, and then 5. So I'm starting with 1, and I'm stopping with 5, and I'm putting them into this function here. So when you square all of those and add them up, you get 55. So that's the sum of that sequence from the first term to the fifth term. So for part B, here we have a fraction. Doesn't matter, the rules still apply. I'm going to start with 3 though this time, and then go to 4. So notice how my variables changed. That's okay. Like I said, it could be any variable. So this means I'm going to have 1 over 3 plus 1 over 4 plus 1 over 5. And when I add those up, I'll get 47 over 60. And then for part C, okay, this one's written a little bit different. The only thing we're going to do is we're going to take that actual number, I. So I'm really just adding all the numbers from 5 to 10. So I'm going to have 5 plus 6 plus 7 plus 8 plus 9 plus 10. So again, the number on the bottom tells you where you start. The number on the top tells you to end. The sigma tells you you're adding. And then this is your function to get all of these numbers. And when you add that, you get 45. Okay, last one looks really different because there's not really an I to substitute in. It's just an actual number. So that means I'm going to take this number. This number is my function, 2. And I'm going to add it from 1 to 6. So I'm going to have 1, 2, 3, 4, 5, 6 terms. All my terms are going to be 2. So 2 plus 2 plus 2 plus 2 plus 2 plus 2. So basically it's 2 times 6, which is 12. So they'll show you problems like this in your homework, and they're kind of just to make sure that you're thinking. They're trying to make sure you have your thinking cap on. Sometimes students get tripped up by those. So hopefully that's clearer now that this function, whatever it is just the function 2. So it could be like a horizontal line where every y value that you get out is 2. Okay. Now you can do this on your graphing calculator. The next slide explains that. How you have to type in the notation into your graphing calculator can be a little tricky, depends on the type of calculator you have. The directions here are for a TI 83. Most students now have 84s or they have Casios. So we'll take a closer look at this in class. But basically, if you go into the math menu, if you have a TI calculator, if you go into the math menu and then you do option O, that's where you'll find this notation to do a sum and a sequence. And then you have to type in what the actual function is. And then you have to say what the variable is. And then you have to say your starting value and your ending value. And then the value that you, or how you want it taken. You want it taken like one number at a time. Okay. And you can do that if it's a fraction as well. This was in the last example we did, this was example A, and this was example B. I don't know why my pen's not writing. So this was part A, and this was part B. Oh, it's still not writing. Okay. But again, you can go to the math menu and then go to option O. And then if you go to sum and sequence, you have to type in 1 divided by j for the fraction, and then you have to do the comma. Your variable is j, you do another comma. You're starting at 3, you're ending at 5, and then you want the numbers taken one at a time. And then this little notation at the end just says that you want to convert it to a fraction afterwards. You don't have to put that on at the end. The calculator would give you a decimal, and then you could convert it into a fraction. Okay, so if you want to do these in your calculator, you can, but it takes a lot of time to type them in. So sometimes it's easier just to do them by hand. And then there are some rules for sigma notation and for the properties of sums. And they're just little shortcuts where if you have a sum of your functions, you can make each one its own individual sigma notation, or vice versa. Same for subtraction. If you're subtracting two functions, you can break them down into their own sigma notation, or you could combine the sigma notation so that you're subtracting the functions. And then here, this is really useful because if you have a constant, a c value, that's out front of the function, you can take that C value out of the function like a greatest common factor. So then you can do the sum of the function, and then when you get your sum, then just multiply it by that constant. Okay? So you might see some problems like that in your homework where they want you to apply those skills. Those should be very easy applications. But our last example here has us writing each of the sums in sigma notation. And this is kind of like what we did at the end of example 5, actually, which was our very first example, where we were writing the function notation, but we're going to kind of combine that with the sigma. So we're going to use our knowledge of yesterday's notes where we were writing a function, and we're going to then use that function as the function that goes on the right side of the sigma notation. Okay, so for our first example here, we have the sum of 1, 5, 9, 13, 17, and 21. So this sum here, you want to just kind of think of it like a sequence, like we did yesterday. And you're going to say that I have 1, 2, 3, 4, 5, 6 terms. So eventually I'm going to have a sigma where n goes from the first term to the sixth term. So that's probably the easiest thing to do first, is to just kind of set up your notation. And then we want to look for our pattern. Now, to go from 1 to 5, you add 4. To go from 5 to 9, you add 4. 9 to 13, 13 to 17 to 21. You're adding 4 every single time. So this is an arithmetic sequence. So we could say, okay, my first term is 1, and then I'm adding 4 every time, so that's my difference, and then I have to do the n minus 1. And then when you distribute the 4 and combine your like terms, you get 4n minus 3. The other way to get that 4n minus 3 is to say, okay, I'm adding 4 every single time. Adding is like multiplication. When you do repeated addition, that's multiplication. So I'm going to multiply by 4, and then plug in your first term and see if you get 1. Plug in your second term, see if you get 5. You're not going to, because 4 times 1 is 4, and 2 times 4 is 8. So the only way you can get to 1 and 5 and 9 is if you subtract 3 from your product. Okay? So remember, there's multiple ways to come up with the actual function, but then when you put it in the sigma notation, you're going to put the sigma out front, and you're going to put the variables that you're using, and then the value that you're starting with, and the value that you're stopping with. Okay, so let's take a look at B. B is the one with fractions. So again, for the fractions, we have to think of the numerator and the denominator separately. We need a function for each. Okay. And in the numerator, I'm adding 1 every single time. And in the denominator, I'm adding 1 every single time. So you could think of that like an arithmetic sequence. Okay, and in the numerator, your first term is 2, and then you're multiplying by 1 every single time. So then you'd have n, and then you'd have a minus 1, and when you combine your terms, you would get n plus 1, actually. Or you could think, okay, my first term, if I substituted it in, would be a 1, and then I'd have to add 1 to it. And my second term is a 2, and then I have to add 1 to it to get 3. And my third term is 3, and I have to add 1 to it to get 4. Okay? And in the denominator, we're also adding 1 every single time, except now my first term is a 5 that I'm starting with. So I'm still going to have n, but then here it'll be plus 4 when I distribute and combine my like terms. Or you can think, okay, I'm adding, so I need an n, but my first term is a 5. So if I put a 1 in here for my first term, the way I get a 5 is I add 4. My second term needs to be a 6, so if I put a 2 in here for my second term, the way I get the 6 is I add 4, and so on. So that's going to be your function, and then you need your sigma. And again, we've got 1, 2, 3, 4, 5, 6, 7 terms. So I'm starting with n equals 1, and I'm going to 7. So that's my sigma notation for part B. And for part C, this one's a little bit different. I'm not adding. I mean, I'm adding in the sequence, but the pattern is not addition. I could add 1, and I could add 2 and add 4, but the common pattern is to times by 2. I would multiply by 2 to go from 1 to 2, multiply by 2 to go from 2 to 4, and 4 to 8, and 8 to 16. So since I'm multiplying by 2 every single time, this is where I need my base to be that 2, and then I'm going to have n for my exponent, and then I want to check it. If I put my first term in, I put a 1 in because it's my first term, but 2 to the first power is 2, and I want a 1. So then I would have to subtract. I'm going to subtract in the exponent here. So if I do a 1 for my first term, 1 minus 1 is 0, 2 to the 0 power is 1. And then for my second term, I'd put a 2 in here. 2 minus 1 is 1, 2 to the first power is 2. This is my third term, so I put a 3. 3 minus 1 is 2. 2 squared is 4. Okay, so that's the pattern for this sequence. And then I want to show that I'm summing it. And here I have 1, 2, 3, 4, 5 terms. So I'm going n equals 1 to 5. Okay, now part D, I think we've seen this this pattern in the previous day's notes. And there's a couple different ways that you could think through this. To go from 1/9 to 1/3, you'd have to multiply by 3. To go from 1/3 to 1, you'd have to multiply by 3, and so on, and so on. So this is a geometric sequence because we're multiplying by a common number every single time. We're doing repeated multiplication. Same thing in part C here. We're doing repeated multiplication. So my first term is a 1/9, and then I'm multiplying by 3, and then I'm going to have the n minus 1 as my exponent. And we could have done that here for part C as well. My first term is a 1, and then I'm multiplying by 2 every time, so then I have the n minus 1 in my exponent. Okay, that's probably an easier explanation for how we got the 2 to the n minus 1. And that works much nicer here for part D when we have to write our sigma notation. I'll write it off to the side so we're not as smushed. I've got my sigma. I've got 1, 2, 3, 4, 5 terms. So I'm starting with my first term, and I'm going to the fifth term. And then I'll have 1/9 times 3 to the n minus 1. Don't multiply the 1/9 and the 3, because the 3 is being raised to an exponent. It's got an n minus 1 power. Okay, so don't try to simplify it and multiply the 1/9 by the 3. That's not a legal mathematical operation. Okay, and our last one is to start at 3 and then go to 6, 11, 18, 27. So we're not adding the same amount every time, but we're adding to go from 3 to 6. We could add 3 or multiply by 2. To go from 6 to 11, we're adding 5. So we're not multiplying by 2, and here we're adding 7. So this is going to be one of those patterns where we have a double pattern. Because I'm adding 3, 5, 7, 9, I'm adding odd numbers. So then I'm really adding 2 every single time here to go from one step to the other in the pattern. So remember when I have this double pattern where it's double addition, where each layer has this addition in the pattern, then that's where my base is going to be an n and my exponent is going to be a 2. And then you want to check it. So if I put a 1 in for my first term, 1 squared is 1, I want a 3 for my first term. So I'm off by 2. If I put a 2 in, 2 squared is 4, I wanted 6. Again, I'm off by 2. If I had to put a 3 in, 3 squared is 9. My third term isn't a 9, it's an 11. So I'm off by 2 every time, so I need to add that 2. And then I'll stick my sigma in the front, and I'm going from 1, 2, 3, 4, 5, from 1 to 5. So I put 1 on the bottom and 5 on the top. Okay, so for part A and B, that's good review of the arithmetic sequences and how you can write the notation for the arithmetic sequence. C and D, that's good review of what you can do for a geometric sequence. And then E, that's that double addition type of a sequence. Okay, so we're reviewing a little bit from yesterday, and then we're just adding in that extra layer of the sigma notation. So when you first see the sigma notation, it seems a little confusing and a little intimidating or daunting, but it's not really that bad. It's actually kind of cool. It's just a cool notation. So practice this homework. Again, they're all odds, so you can check them in the back of the book. Remember, the answers are worked out on the class website. And if you have any questions, come on in and see me before school.